So this topic is about angular momentum, which is going to be the last topic from this chapter. The angular momentum is defined as inertia of rotation of rotating objects. Okay, so if we still remember the definition of linear momentum, which equals to mass times velocity. So if I replace mass by rotational inertia, replace velocity by the angular velocity, so we have angular momentum definition. For an object that is very small compared to the radial distance to its axis, so the angular momentum becomes mass times tangential speed times radius. Okay. If we know angular momentum definition, I want you to think about linear momentum. So what can change linear momentum? We learned about impulse momentum theorem, right? So if you have impulse, that means if we apply force over a certain amount of time on the object is going to change its linear momentum. So the change in momentum equals to impulse. Similarly, if we need to change the angular momentum of an object, so we need to have external net torque applied to the object. So then we have rotational version of Newton's first law. An object or system objects will maintain its angular momentum unless we have external net torque acting on it. Okay. What if we don't have net torque? If there's no net torque, then the angular momentum of the system remains constant. Similar to what we learned before for linear momentum conservation principle, if we don't have net force, external net force, then the linear momentum of the system is conserved, which we learned from chapter 6. Okay. So if we have no external net torque, the angular momentum is constant. So one typical example we can think about is like for this person. So when the person pulls the weight inward, okay, the rotational speed increases. Why? Okay, assuming we don't have any external forces acting on it, there's no frictional force, there's no external torque, then the angular momentum should be conserved, right? But initially when he extends the weights outward, remember the rotational inertia depends on two things. One depends on the mass, the second depends on the mass distribution. When he extends the weight outward, the rotational inertia actually is bigger than when he pulls the weights inward. So we see a big I over here and small I over here, since the angular momentum is conserved, right? So then the angular velocity of the first case initially would be smaller, and then that's why his rotational speed increases. This also applies to figure skaters. Have you ever watched a figure skater? A lot of people, like, for the last finale posture, what they do is they are going to spin and then spin fast and faster. And why they can spin faster? Actually, they don't have to do a lot in order to spin faster. Based on angular momentum conservation principle, initially when he or she starts to spin, okay, he or she has to extend the arm and then start to spin. So when he or she extends the arm, rotational inertia is bigger, so the initial angular rotational speed or angular speed is smaller. But since the angular momentum is conserved, so that's why when he or she pulls the arms in, so rotational inertia becomes smaller, and then the angular speed automatically becomes bigger. Okay, so that's another example. Actually, you can think about the application of rotational inertia, the application of rotational momentum conservation principle.